you should have gotten a little prompt there saying that the meeting is being recorded. So that is just so that you know that that's happening. So with our administration, like here, I've moved because of connectivity issues some people are having, I moved it so that the homeworks will be due on Wednesday afternoon or evening. And so that'll give us homeworks 7 and 8. And then we'll hopefully get back on schedule. I believe all of 7 and 8 are up on YouTube. Let's go ahead and share this one right here, share, and go to YouTube channel. So we have all of chapter 8, but it's not annotated. I will fully annotate that as we move forward. I didn't have time with my other classes, but I have all of these, the first 3 parts of chapter 9, and they have video as well as talking through them. So I believe I only have a couple more of those to do, and then those will be uploaded to that station. I'm actually going to look at my Finder and look at how many more of those videos I need to do. Okay, so let's see. I've done all but I need 2 more. I need di and polysubstituted benzenes and phenols. And so the part 9, chapter 9 there will be complete by this afternoon. And so then those homeworks will be due. Oh, sorry, I have a chat here. The homeworks will be due. Okay. So I should have those 2 done this afternoon and uploaded so that we can finish with chapter 9 and start working on chapter 10s, which is this amine. We're only going to have a total of 2 videos for chapter 10, and then chapter 11 will start on after that, which is, I want to say, spectroscopy. And so there'll be probably 5 chapters on spectroscopy. So we'll start doing those later. I did get a chat question about when the labs are due. The email I sent out this morning is correct. We will upload the Skittles lab by Thursday, which is our normal lab time. The post-lab response is already uploaded to your Dropbox and Trax. And so you'll need to download that and either transfer it electronically or actually print it, write it down, and then upload it back to your Trax box by Monday at 5 p.m. Okay, so I'm going to try to get the next labs posted earlier. So the next lab will actually be due next Thursday, and then the last lab will be doing the following Thursday. That way, all of our labs will be done, and so that we will not have a lab final and we will not have lab checkout, and so that we can just go ahead and stop worrying about our lab and just focus on the class and all your other classes and get those things complete as possible in the time we have remaining. Okay, does that answer your question about the labs? Okay, great. All right, so I'll keep that session open there. Let me go ahead and close that. Go back to stop sharing. Okay. So do we have any questions about reactions of alcohols? I can actually pull those slides up and write around on them as needed. Let's start with the chapter 7. I know that wasn't, I'm sorry, chapter 8, that wasn't fully annotated. So I'd like to, if you have any specific questions about that, I can go through either the nomenclature. The key things in alcohols is recognizing the fact that you have in an alcohol a carbon-oxygen-hydrogen bond, and that gives us its properties because that oxygen-hydrogen bond can do hydrogen bonding. The ether is the carbon-oxygen-carbon bond, and that means it has no hydrogen bonding. And then the thiols are that carbon-sulfur hydrogen, but the bond between the sulfur and hydrogen is not polar enough to hydrogen bonds. So that's why its properties are different. Even though it looks analogous, the fact that the sulfur is down one row and is bigger, it has less electronegativity on it, therefore there's a less polar bond, and therefore the properties don't change as much. But I thought it's a really nice contrast between the alcohol and the sulfur, even though they're one row apart, the fact that the electronegativity changes enough that you see that change in the hydrogen bonding. I think that's the most valuable aspect of, what alcohols are and why they are that way. The next most important thing, of course, is the reaction of them. Here, I'm going to pull up the slides from there. Let's see, it's going to be over here, share screen. This desktop here with chapter 7 PDF. Okay, oops, that's chapter 7, not chapter 8, sorry. Okay, so, so that's the first most important thing about these alcohols. And this, I have a question here in the chat. Let's see, with regards to, okay, how do alcohols react with active metals? That's a really good question. Okay, see, it comes down to that fact that we have that hydrogen bonding actually as well. Let's continue down here. We're going to go through that hydrogen bonding and go to the reaction of metals. Now, because the alcohol can act both as an acid and a base, if we lose the proton, it can act as an acid, but it has lone pairs. So when you think about it, that makes it a Bronsted-Lowry base because it has these lone pairs to work on. So when we react it with active metals, what we're actually doing here, and here's the active metal slide on here, is when we have lithium metal, sodium metal, or potassium metal. Let's see, do I have can I annotate on here? Yeah, I can. Okay, great. The lithium, sodium, and potassium, when they are metals, they are very reactive metals. They're on the, the far left of the periodic table, and they would much prefer to be salts like this positive charge here. So what they're going to do is they're actually going to take an electron away from it, and it's going to donate that electron to our alcohol, okay? Now the oxygen already has electrons on it, so it doesn't need the electrons. So what happens is the sodium, when it loses the electron, turns into sodium. Let's see if I can do this, plus. And when it tries to donate the electron to the oxygen here, the oxygen already has this lone pair, and then this pair of electrons going to the hydrogen. So what it does, instead of donating it to the oxygen, because the oxygen has that full octet, it actually ends up donating it to the hydrogen. And when it donates that to hydrogen, what it ends up with is you have a hydrogen right here minus right here. Now this hydrogen minus can act as a base and will react with the hydrogen plus on another molecule to give us a hydrogen plus here. And so these electrons end up creating this bond between it to make the diatomic hydrogen. And then that way we have the sodium plus and the electron on the oxygen here creating a salt. So now we have the methanol, or the salt of the alcohol. Sometimes we call that an alkoxide, because the alkoxide is basically just a deprotonated alcohol. And then we have the sodium salt here, plus hydrogen. So what's happened is really an electron has been moved from the sodium to the hydrogen, and that hydrogen reacted with another hydrogen plus to give us our material here. So what you have to end up doing is, for every 2 equivalents of alcohol, you can react with 2 equivalents of sodium salt to create 2 equivalents of the sodium salt here. I'm sorry, sodium metal to sodium salt. And then that creates 1 equivalent of this hydrogen here. Okay, so that generation of that electron is being transferred to the hydrogen here, when it transfers the electron to the hydrogen here, these will each have one electron on them, and that can form this bond here. Remember, a sigma bond has 2 electrons in it, always. And so it's forming two of those, one electron from one sodium, one electron from the other sodium, gives us 2 electrons to create this hydrogen-hydrogen bond. And so what's electronically, if we think about in Gen Chem, the sodium is being oxidized because it's giving away electrons. The hydrogen plus is being reduced, giving us a hydrogen with this the sigma bond here. And therefore, we actually have a redox reaction. Now, once this hydrogen forms hydrogen, it goes away as a gas. So it's irreversible. It makes that salt, and that stays there. Okay. The other cool thing is because we've made this right here and we didn't form water, it's now irreversible and it's somewhat stronger than hydroxide. Because remember, when hydroxide is a base, but when it reacts with an acid, it creates water. And when it forms water, water can act as an acid or a base. Okay, so this is how alcohols react with reactive metals to generate that alkoxide system. So it's all about transferring an electron from the metal to the hydrogen, and that creates our nice stable salt. Okay, does that answer the alcohol reactive metals question? Okay, great. So let's do a couple other reactions associated with our materials here. Oops. Let's see, I gotta erase all that now. Erase. It's one of the things I like about when I do the annotations, the writing actually moves along with the thing as I move it along, but let's do that. Okay, so one of the primary reactions we have is to actually convert our alcohol to our halides. Remember, we actually made our halides by converting them from alkyl halides to alcohol. So that reaction is reversible. And the way it's reversible is how much acid we add. So the more acid we add, and if we remove water, it's going to go in this direction here. And we're going to create our alkyl halide from the alcohol. But now if we have very little acid and a whole bunch of water, we can actually drive it back the other way. So it's the same reaction, except that we're forcing it one way or the other by having a lot of acid on this side will give us our alkyl halide. A lot of acid, a lot of water on this side will take it back to the alcohol. So it's the same reaction, the same mechanism. It's all about how much material you have. Okay? Now, this works best with tertiary alcohols. And if we think about it, working with tertiary alcohols, that means we're probably forming a carbocation because the tertiary carbocation is the stable carbocation. Okay? I have to erase this before I move on. Okay. So the other reaction I want to make sure we talk about while we're here is the dehydration of alcohols. Okay. So in the case of the oh, no, that's an alcohol to form the alkyl halide. Okay. The dehydration of alcohols. And this right here that's supposed to be a beta elimination. What beta elimination means is that there's a hydrogen 1 carbon over from where the alcohol is. Okay. So when we do this, we think about it as if all we're doing is dehydrating an alcohol, that means we're removing water. Some of us are seeing you annotate on the YouTube screen. Oh, let me close the YouTube screen. Let's close that. Okay. minimize that. And quit that. Let's quit that. All right. Can we see annotation on the PowerPoint slide now? We want to still see YouTube. Okay, let's see. Let me stop sharing and bring the window to the front. Okay. All right, let's do that. Let's escape. Okay, let's go back to here. Let's screen share. Let's screen share the PowerPoint. And I see PowerPoint now. Okay, let me open the chat again. All right. Let's see. All right, fixed. Still. All right, can everybody see this dehydration of alcohol slide now? All right, looks fixed. All right, yeah. So apparently I shared the wrong screen. So should I go back to the active metals one, or should I just stick with the dehydration one? Okay. All right, so after the reactive metals one, the reaction of alcohols with acids is the next most important reaction, because we can go back and forth from alkyl halides to alcohols. And it's all about trying to get them to go back and forth based on how strong your acid is and how much water you have there, okay? So let's go back to the dehydration of alcohols. And so right here, this doesn't show up all the time, but this should be, let's see if I can bold it right there. So that should be beta elimination. What beta elimination means is that there's a hydrogen one carbon over. The adjacent carbon has to be one carbon over from the OH, okay? So if we have primary alcohols, this takes really high temperature and high heat, the high heat and a catalyst, because it's very difficult to get that water, the water molecule or the OH to leave. Now, once you go to a secondary alcohol, it becomes a little bit easier. So it's slightly lower temperature. And in a tertiary, it's even a lower temperature. And if you can think about it, that makes, because the idea of forming a tertiary carbocation makes it a little bit easier to remove that. So let's go and look at that dehydration. So if we just take ethanol right here on this first one, and let's see if I can switch over to red here. There we go. Ethanol, that's a primary alcohol, right? So this carbon right here only has one other carbon on it, so that makes it a primary alcohol. And so we have very high heat, 180 degrees. And what that does is that loses water and it creates ethylene. So when we dehydrate something, we just remove something. Unlike the alkyl halide reaction, where we're substituting an OH for a halide, we're actually just eliminating water. And so what that's going to do is that's going to always give us at least a double bond, sometimes a triple bond, but in this case, a double bond. Now, if we look at the cyclohexanol now, and I'll draw that in blue here, this is a secondary center because it has two carbons bonded to it, so that's a secondary alcohol. So it's a lower temperature, only 140 degrees, but it does the same thing. It creates this double bond on it right here. Okay, so once we get down to this tertiary alcohol, let me change colors again to a green color here. This has 3 carbons bonded to that. Notice it takes place at 50 degrees. That's just barely over room temperature, okay? So that gives us much easier to form these. So think about, you know, primaries, very high heat, secondaries, not as bad. The tertiaries are getting pretty easy to go ahead and dehydrate. Okay, erase. Erase, erase, erase. Okay, and then moving to the next slide here. Now, we can predict which alkene we make by the fact that we always want to form the most stable or most substituted bond. So we want to give the greatest number of substituents to that double bond formed. Okay, remember back with alkenes, okay? If we had an alkene at the end of a chain, that's the least stable system. And then if we had an alkene in the middle of the chain, it preferred to be a trans alkene, and then a little bit less stable is the cis alkene because of sterics. And then if we had 3 things on it, it was even more stable, and 4 things on it, it was even more stable. So what we're looking for is when we dehydrate these alkenes, if we can form a more stable compound with more substituents, we will. And that's called Zaitsev's rule here. So when we look at this right here, we have a possibility. We have a secondary carbon here, which means we're using high heat, probably 100 degrees or more. We have the possibility of, we have a hydrogen here. There's a beta hydrogen here, and there's a beta hydrogen here, okay? Now, if we think about it, there's 3 beta hydrogens on this side and 2 beta hydrogens on this side. So, there's 1 more beta hydrogen. It might want to eliminate on this side first, right? So if we eliminate on, actually, what I'm going to do is I'm going to draw these as blue. These hydrogens over here, if this hydrogen over here, okay, and we have a total of 3 of those right here, that's going to give us this terminal alkene right here, okay? And there's 3 of them there. There's, a total of 3. And you're thinking, oh, well, there's more of them here. It might want to go this side, right? Okay. But if we look at this one over here, it has 2, okay? So when we lose this OH right here, when it's going to either take this hydrogen or it's going to take that hydrogen with us to lose water. What it's going to do is it's going to look at, okay, if I remove this beta hydrogen here, that means these electrons are going to come down in here and form a di-substituted alkene, as opposed to these electrons are going to come over here and make a monosubstituted alkene. So see, this only has 1 substituent on it here, plus the hydrogens. This has 2 different carbons on it, okay? And so it's always going to eliminate where it gives the more substituted one as the major product. So notice we have 80% of it is the di-substituted, 20% of it is the monosubstituted, even though we have 1 more hydrogen statistically available to us, okay? Let's look a little deeper in the next slide here. Okay. And what we can think about as to why it is that the first step in these acid catalyzed systems is always adding a proton, okay? Whenever we say there's an acid catalyst, you want to think, oh, where can I put the proton? And in this case here, we know that we can put the proton on anything where there is a lone pair, okay? And in the case of our alcohols, the lone pair is typically on the oxygen of the alcohol, okay? So we know that we have a proton and we know that we have an acid. So that's the first thing that's going to happen. And that's a fast reaction to give us this oxonium cation right here, okay? Now, what it's done for us is that it's given us something that's a very good leaving group. If these electrons come up here and leave with water, that's going to leave as a neutral molecule, okay? That makes it a really good leaving group. So that's why we want to think about this as, oh, first thing we're going to do is we're going to protonate this to give us our good leaving group, okay? So now our second step is kind of what we'd expect to happen. No, stop notating. There we go. is our second step should be the breaking of our bond to give us our carbocation, okay? So again, this is our good leaving group because it can leave as neutral water right here. This is a nice happy molecule here. And it's giving us our carbocation, okay? Now, okay, now we have to start thinking about stability of our carbocation. If we were to lose the proton on this side to form our carbocation, it would give us our, I'm sorry, not give us our carbocation. It would give us a different material than if we had it the other way, okay? So now the next step in our system is to have the water come in and act as a base, okay? So our water here, oops, I'm not trying to draw a straight line here. All right, our water here is acting as our base and has to remove either the proton here or the proton here. And in this case, it takes the interior proton that gives us our interior double bond, and we regenerate our catalyst here. So notice we started with hydronium ion and we end with hydronium ion. So that means it's a catalyst, it's regenerated in the last step. Okay, so anytime you have an acid catalyzed reaction, protonate something first. You're going to protonate something that makes it a better leaving group. And then when it leaves, you regenerate that proton by having something react as a base. And it's typically whatever gave up the proton in your first step will accept a proton in your last step. Okay? So those are the key steps in the dehydration. Okay? And that same idea of the proton being the first step also happens in your substitution reaction with your acid halides. Okay, let's see. So in your dehydration of your primary alcohol, it's the same thing, except that you typically don't have it leave as the, you don't form the carbocation. What you do form is you form an intermediate with your material here, and now your base comes in and starts to remove your alcohol here. So what we call this is, because the base has to come in, and because otherwise you'd form a primary carbocation, which we can't form. That just doesn't happen almost any time. We have to wait around for the base to come in and remove that beta proton to eliminate. For both secondary and tertiary alcohols, you form the carbocation intermediate. For primaries, you have to wait for the base to come in and pull that proton off. So there's only 2 steps in a dehydration of a primary alcohol, where there's 3 steps in the dehydration of a tertiary alcohol. Okay. So again, this is a reversible reaction. We can go from an alcohol to an alkene and from an alkene to an alcohol. And it's all about how much of whichever one you have there. If you're taking away water from the system, let's say you're doing it at a high heat where you're boiling off the water as it goes, you're going to drive it to the alkene. But let's say you actually have it in a water system and you keep adding a large amount of water with just a little bit of catalyst, you're going to drive it to the alcohol. Let's say you have it something else. You have a whole bunch of HCl bubbled into the system and very little water. Well, what you're going to do is you're going to drive your alcohol to the alkyl halide, or you're actually going to add the HCl across that double bond. It's all about what thing you have a whole bunch of is going to help drive the reaction to the system. So we can actually even put a bigger part of the triangle here, as if we had HCl up here, and if we're removing water, we can drive it to the alkyl halide, or we can drive it to, we can react either one of these to drive it to the alkyl halide. Okay, let's see. So then the last reaction we have here is we have what we can call an oxidation. And so what that means is our alcohol has one oxygen bonded to a carbon, okay? So, and it's bonded once. So we can take that and add additional oxygens to the thing or bond the carbon multiple times to that oxygen. So if we take a strong oxidizing agent, and the classic one, we call this the chromic oxide or chromic acid system right here. What it'll do is it'll add another oxygen and then add a double bond to give us this carboxylic acid right here, okay? So it's gonna oxidize it, so there's a total of 3 bonds to oxygen on the single bond of carbon, okay? However, this carboxylic acid is a very good functional group, but sometimes you don't wanna oxidize it down that far. And so we have a special reagent right here that we use where we call it PCC. And we can take a primary alcohol right here with this compound here. And what we've done is we've taken the chromium material that we had before, but we're making it a little bit weaker by adding this chloride ion to it. By adding this chloride ion to it and adding this pyridine ion to it right here, what we've done is we've decreased the ability for it to oxidize something. So instead of taking it all the way down to where we have a total of 3 bonds of carbon to oxygen, as with the carboxylic acid right here, we actually only end up with these 2 bonds to here, and it creates another functional group called an aldehyde. So this is partially oxidized. And then if you took another oxidizing agent, you can oxidize it even further down. But this is a really good way of, in fact, we typically only just call it PCC, to stop it at that aldehyde. A lot of nature's interesting smells are aldehydes and ketones or esters. And so it's really used a lot in biological systems. It's also because it can be easily oxidized, we use it in a lot of biological systems. And we have that in another chapter. Okay. About aldehydes, not this oxidation. This oxidation's here. Okay, let's see. And then we go on with ethers. Ethers really don't have many reactions. They're very stable. And so that's why we use them as solvents a lot of the time. The only difference there is that really this one right here, this ethylene oxide, is a very reactive ether because it has a small ring. We can break that ring open. Other than that, most of the other ethers are very poorly reactive. And so that's why we really don't have any reactions in this area, because the only reaction we have is the one with the epoxy, okay? And because they don't hydrogen bond, their boiling points aren't as high. But we do have that reaction here. So making these, we can ring open this to give us diols, and we can ring open to give us other things as well. So here's the other thing. We can open that ring because the ring is so small and so tight, it wants to be sprung open. So if you have a nucleophile come and attack this side, because it's the less crowded side, right? Because there's a methyl group here. Any nucleophile, which means like this has those 2 lone pairs, I mean the lone pairs on nitrogen, this has lone pairs on oxygen, and this has a negative charge on sulfur. These are going to come in and open up that ring to give you the system, okay? Now notice the nucleophile is always going to come on the least hindered side. If you already have a group here, the nucleophile is going to come in on the other side, giving you the alcohol on the more substituted side, always. But again, that's the only reaction that our ethers do. Let's see. And our thiols are actually used extensively in protein chemistry, and we'll get to that a little bit in biochemistry as well. But the most interesting reaction we have in the thiols is the idea that we make this dithiol bond right here. So just by reacting it in air, sometimes you can take this sulfur compound here and create a sulfur-sulfur bond. The sulfur-sulfur bond is the disulfide bond, and it's used a lot in protein chemistry. It's used in making hair curly or straight. If you want to make it curly, you break that disulfide bond, curl it up, and then remake that sulfide bond. If you want to straighten your hair, you break that disulfide bond, straighten it out, and then remake a disulfide bond. The other interesting part that this chemistry happens is in tires. It'll make a sulfur-sulfur bond in tires, and that's why tires wear so well, is that because they're constantly breaking and remaking these sulfur-sulfur bonds. And so I just always find it amazing that you can take a plastic material and drive on it for 100,000 miles and it'll still be flexible and pliable and do everything that tires do. You know, and I'm a polymer chemist. I still think it's amazing. So, okay, so that's the end of alcohols and thiols. And on Wednesday, I will also tackle benzene, but I can start looking at conjugation. Does anybody want to talk about conjugation and resonance stability? Because I have some time for that. All right, let me erase this here. Okay, actually we're to the point where if you have any specific questions, go ahead and ask them now. I will answer them as we go. If you don't have specific questions, I'm going to pull up the other slides and talk you through resonance stability here. Okay, let's don't annotate. Let's stop sharing. Let's go to PowerPoint and close this. Don't save, open another one. Chapter 9. Go over to Zoom and share my screen, PowerPoint, share, benzene and its derivatives. Let me get back to where I can see chat. Okay. All right, so so I've done most of my research on benzene and benzene derivatives, so I find these things to be quite fun. And so the key that I think we need to talk about here is the idea that in benzene ring, you really don't have just alternating double and single bonds. That really does not exist. What happens is that this is a bond and a half, this is a bond and a half, this is a bond and a half, this is a bond and a half. And the idea that those are all sharing that partial bond character is what gives it its stability, okay? So, and I think in the diagram we have below here, the idea that demonstrates that resonance stability, I think is the really cool thing is this diagram here about the hydrogenation, okay? So if we think of cyclohexane as our baseline, right? So it has all the exact same bonds except for with cyclohexene here, we have a double bond. And in this theoretical benzene over here, we have 3 isolated double bonds, okay? So if we call this energy 0, or this is our starting point right here, and we took a double bond in this ring, and we tried to hydrogenate it, it would release 120 kilojoules per mole of energy, okay? So that's how much more energy is stored in this material than is stored in this material, okay? So what we're basically saying is that double bond is storing energy in the system, okay? So all the other bonds, you know, they do have energy, so it's not exactly absolute 0, but relatively, the difference between these two with just this double bond forming is that amount. So if one of these double bonds right here is the equivalent to 120 kilojoules per mole, then that means that if we had 3 of them, it should be 360 kilojoules per mole released as heat when we hydrogenate it, okay? So it has to release the heat for this bond, and this bond. But when we actually measure it, it doesn't do that, okay? When we actually measure the energy, all we see is the release of 209 kilojoules per mole. What that means is, because we don't have isolated double bonds, because they're not just independent and they're not interacting with each other at all, they're actually interacting with each other significantly, about 151 kilojoules per mole of interaction between them to help stabilize that. Now, that energy is what gives us our reactivity, okay? That saving of energy by the sharing, that saving of energy by being constantly dynamic and shared is what's giving us our reactivity in the benzene systems, which I always find really, really cool. So let me show you how that kind of manifests itself in the compounds here. So what we figured out early on is that to have this stability, to be able to share in a way in which these things were happy, they had to undergo certain rules, okay? So the 4 rules that a compound must have to get this energy of stability is you must have something in a ring, okay? You must have 1 p orbital on each atom in that ring. Okay, now I'll show you why in a minute. We have to actually have those p orbitals kind of line up on each other, okay? If these p orbitals have to line up on each other, that means the ring has to be planar or nearly planar. If we can get a ring to have bonds on each of the have a p orbital on each of the atoms and be nearly flat, all those p orbitals will overlap, and they'll overlap evenly, okay? Now, the last rule is the number of electrons required, okay? Because of the way they're shared, if you have the wrong number of electrons, it can't do a full share. It will alternate back and forth between 2 things. And we actually call that anti-aromatic, but we're not worried about that right now. What we have to do is have a certain number of electrons. And this was actually derived experimentally, not by theory, but they figured out that it was 2, 6, 10, 14, and 18. The most important for us is going to be 6, because 6 is what happens in most of the compounds we're dealing with will have 6 electrons. So let's go look at this with the next slide and kind of see if these criteria are being met, okay? So the first thing I want to do is talk about benzene. Actually, I want to go back a slide and look at benzene and see if it follows those rules, okay? So if we look at this diagram of benzene here, let's see if it follows those rules, okay? We have each of these carbons right here has a p orbital in it. And so in each of these orbitals, it actually has a single electron in it. So we have 1, 2, 3, 4, 5, and 6 electrons. They're in a ring and they're flat, okay? So this satisfies all 4 rules to make it aromatic. And because it satisfies all 4 rules, it can perfectly share all those electrons above and below the rest of those sigma bonds. Remember, all the rest of these bonds are sigma bonds, and these are our p orbitals overlapping to make better than just a double bond. It's making this overlapped continuous double bond, okay? That's resonance stability, is a continuous double bond system, okay? So let's see if other things satisfy this kind of, these kind of rules here. So let's go back to our heterocycles, okay? So in our benzene ring, we only had carbons in there, right? So, but carbons aren't the only ones that'll satisfy this rule here. If we take out one of the carbons and replace it with nitrogen here, and notice this nitrogen is double bonded to a carbon here, meaning that it had to have a p orbital available to it, and it has 1 sigma bond here, 1 sigma bond here, and then a lone pair sticking out, okay? But it still has a p orbital, and that p orbital has 1 electron in it. So each of these carbons still has an electron, so that satisfies all 4 rules. It's planar, it has a p orbital, it has 6 electrons, and it is in a ring, okay? So that means that this pyridine is an aromatic compound. Now we call it a heterocycle because hetero just means something different than carbon. So it can be nitrogen, sulfur, or oxygen, as long as it forms a p orbital, okay? Now, you can have more than one substitution here. In this case here, we have a nitrogen, but then we have two nitrogens. Notice they both still have a double bond with a carbon, and because they both still have a double bond with carbon, that means they both have p orbitals. And so we have a total of 6 electrons in a ring, planar, with overlapping p orbitals. Therefore, this is also an aromatic compound. Okay. Notice again, right here, we still have the 2 electrons in the lone pair are sticking out where the hydrogens would have been on the carbon. They're sticking out in the same plane as the hydrogens around the outside. Okay. So that's why those also are considered aromatic. Okay. And we don't have to have 6 atoms in the ring. We just have to have 6 electrons in the ring. So let's look at something that's 6 electrons in the ring, but not 6 atoms in the ring, okay? And the classic ones are this one right here, furan and pyrrole. So in furan, sorry, we have an oxygen, and we have this double bond here. Now notice we have a lone pair on oxygen and a lone pair on oxygen, and we have 2 sigma bonds, okay? So we have our p orbital on this carbon, a p orbital on this carbon, a p orbital on this carbon, a p orbital on this carbon, okay? And one of the lone pairs is going to hybridize to be a p orbital, while the other one stays hybridized as an sp2, okay? So this is going to be our 2p, and these are our sp2 over here. What does that mean? We have a lone pair in this p orbital, okay? So we have 1 electron here for carbon, 1 electron for carbon, 1 electron for carbon, 1 electron for carbon, but 2 p electrons on that oxygen. Ooh, so now we have a 5-membered ring, but it's flat, it's in a ring, it has 6 electrons, so it satisfies all 4 rules of aromaticity. Therefore, this is an aromatic heterocycle because it has oxygen in the chain state. Let's see if we can do that for this other one. Let's replace oxygen with nitrogen here. Now, nitrogen likes to have a total of 3 sigma bonds, and it does, but it also has a lone pair on it right here. Remember, most of the time, nitrogen is trigonal planar. Pyramidal, right? Trigonal pyramidal. So we have 1 electron for this carbon, 1 electron for that carbon, 1 electron for that carbon, 1 electron for that carbon. But now we have 2 electrons here in an orbital here. It's going to rehybridize to become a 2p, which gives us a total of 6 electrons in a ring that's flat. So it satisfies the aromatic rule, and therefore a 5-membered ring can be aromatic as well. Okay, so it's all about satisfying the 4 rules: ring, planar, p orbitals, and the correct number of electrons. It has to be 2, 6, 10, 14, 18. But for most of the ones we're doing, it's going to be 6. Okay, and these happen in a lot of different organic compounds. And then that goes on to the naming of benzene, which we'll do on Wednesday. Okay, any last questions there? I think that if you can understand that those are the electrons that are above and below that plane and are perfectly shared there, that's going to lend it to why aromatic rings don't act like isolated double bonds. That sharing, that following all 4 of those rules for aromaticity is what gives us its unique reactivity. Okay? Any last questions before we head out? Again, I'm trying to lean out one email a day. Hopefully I'll have the rest of the stuff posted soon. And if you have any questions, go ahead and email me. We can set up private FaceTiming if at all possible. Tomorrow afternoon, I will be filming the lab for this class. So tomorrow might be a little spotty, but after that, it should be all set. Okay. All right, any last questions in chat before we go? Okay. All right, I'm gonna stop sharing here. You guys go ahead and have a good day. Again, homeworks are due this week, so go ahead and kind of try to finish those up. And let's keep on keeping on. All right. All right, I'm gonna stop recording and